So one slightly different method that's used for analysis is what is typically called the force method of analysis, sometimes called the flexibility method. So essentially for this, what you do is you remove one of the supports temporarily, figure out what the loads do to the displacement, and then you remove all the loads and add in the force from the support back, and that'll give you a certain amount of displacement. And then we know that essentially this displacement here needs to be the same as this displacement here. So we can do that, and then we can, based upon that, we can solve for what our reaction is at FB, and then from there, based upon our equilibrium equations, we can solve for what our reaction is at A. So yeah, you'll get a statically determinate problem with a certain amount of deflection, and then you'll get another statically determined problem based upon that reaction. So again, we just know that these two need to be equal because they need to cancel out. Because otherwise, these two fictional things wouldn't add together to result in the actual loading situation. So again, displacement based upon the load is just going to be based upon the load times the distance over which the load is acting. So again, that's going to be the actual stretch is only going to be based upon this distance here, because this distance, this section here doesn't have any stress in it. And then of course AE, and then our dB here, our displacement due to the reaction at B, is just going to be based upon the magnitude of that displacement times the overall length, because again, in this scenario, FB is at the bottom, and so it's causing displacement over this entire length. And then E, obviously, add these two things together, you can cancel out AE, and then you can solve for FB by just dividing by L, and yeah, then you get your FB in terms of P, the length between A and C, and L. And then once you have that, you can plug that into here, and then solve for FA. So the other thing that we want to be concerned about, one other thing we want to be concerned about is what we call thermal stress. So I put stress in quotes because really temperature changes cause strain. There's a thermal strain, and sometimes that strain causes stress in the body, but it doesn't directly cause thermal stress per se. But anyways, when something heats up, the molecules in it, they start vibrating faster, and they kind of, because they're vibrating faster, they move away from one another, basically. So generally speaking, the hotter something gets, the more it expands. And there's a few instances where that's not the case. Like for example, water. Water has its maximum density at 4 degrees Celsius, I believe. So once it starts cooling from there, and it starts to, especially once it starts to freeze, it expands more. And that's just kind of due to the nature of the crystalline structure. It's a bit weird, but for most materials, especially most materials that you will be building stuff out of, I don't expect most engineers to be using ice. At least I don't expect most mechanical engineers to be using ice as a structural component. I suppose there's some weird civils out there who might, but they're weird. Yeah, for stuff that you'll be using, if it gets hotter, it's going to expand. If the temperature decreases, it's going to contract. So if we're talking homogeneous and an isotropic material, then this expansion is linearly related to the temperature change. Now, again, this is an approximation. It is approximately linear related to the temperature change. Technically speaking, the linear coefficient of thermal expansion for a lot of materials isn't necessarily constant with temperature. So realistically, what you actually need to do is you need to be integrating this over the temperature range. Usually that is a level of detail that's a bit beyond what you need. It's a level of precision a bit beyond what's necessary. For the most part, you can approximate it as being linear over a fairly wide temperature range. So the units for this coefficient it's a material property. It's basically strain per unit temperature change. So its units are per degree Fahrenheit or per degree Celsius or per degree Kelvin, however you want to. Per degree Kelvin or per degree Celsius is the same thing, because they're 1-to-1 in terms of change. You can look at it like that, or if you want to kind of keep it in terms of strain, it could be like inches per inch degree Fahrenheit, or millimeters per millimeter degree Celsius. That gives us the strain. Change in temperature is obviously going to be in terms of either Fahrenheit or Celsius, and then the original length of the body will be based upon whatever unit system we're working with, millimeters, meters, feet, whatever. And then that'll just give us the deflection in terms of it'll give us a thermal expansion or contraction. So if the thing is free to expand or contract, then you can use that equation to figure out what that deflection will be, and then there won't be any stress induced. It'll shrink or it'll get bigger, and that's all that'll happen. No stress will be induced as a result. If, however, this it is a statically indeterminate problem, and this thing's kind of mounted between two things, or if it's held in place in a manner that doesn't allow it to expand or contract, then the thermal displacement will be constrained by the supports, and we get what a lot of people call thermal stresses. So the change in temperature causes a thermal strain, and those thermal strains may induce thermal stresses if they're constrained. So if the member that you're talking about or the body that you're talking about isn't allowed to do whatever strain it would otherwise do, then thermal stresses get introduced in order to counteract that strain. They do sometimes arise if we're talking non-homogeneous or materials or anisotropic materials undergoing temperature changes. So your carbon fiber reinforced polymers are a good example. The polymers and the carbon fiber have different coefficients of thermal expansion. So the material as a whole isn't able to expand and contract at the same rate. So there's some stresses that get introduced as a result of that. Anyways, so these thermal stresses can be calculated based upon what deflections they would have caused. So let's look at an example here. We got this got the steel bar, and it is a square steel bar, well, a square cross-section steel bar, and it's fitted between these two rigid supports. And then we increase the temperature. So we increase it from 60 to 100, and we want to figure out what sort of stresses are induced as a result of that. So if we have this bar here, it's expanding based upon the temperature raise, but it's restrained from doing so due to the supports. Now let's draw a free body diagram of that guy. So again, we've got a bar. We've got By, and we've got Ay, and that's about it for our free body diagram. So we know that By is going to be equal to Ay. We just don't know what it is because the reactions here aren't being caused by an external load. They're being caused by the thermal expansion of the thing. So essentially, we're going to have to go back to figuring out that the total that the displacement from A to B is equal to 0, but that is going to be based upon the displacement due to the load. I'll call that, there we go. No, sorry, displacement due to the reactions. Let's call that C, or compressive. Yeah. Delta C for compressive. Why not? So that's going to be equal to, PL over AE as per normal, where P is either where P ends up being it's a negative amount because we're going to be working with it's a compressive load. So and the magnitude of that is either By or Ay. Either one, they're the same thing. Times the L over AE. And then we've got our thermal as well. So that is just going to be equal to the original length times the thermal strain. So thermal strain is going to be alpha times delta, no, that looks more like an A, times delta T. It's our thermal expansion, and those two things just need to be equal to 0. So we can just equate that. That plus that is equal to 0. Move the one with the negative term over to the other side, and we get L times alpha delta T is equal to PL over AE. So simple enough here. Cancel out the L's. And we can go and solve for P. It's going to be equal to alpha delta T times A times E. So our load, our internal load is going to be equal to the coefficient of thermal expansion, which we need to look up on our table. So we've got a couple things we need to look up on the table, so let's do all that all at once. So we're working with the A36. So first off, well, we need to know E, so that's 29 times 10 to the 6 psi. I'll write that down. E is equal to 29 times 10 to the 6 psi. We also need to know our coefficient of thermal expansion, so that's over here. So for steel, at least that type of steel, We're working with 6.60 times 10 to the negative 6 per degree Fahrenheit. .60 times 10 to the negative 6 per degree Fahrenheit. And while we're at it, so our A is going to be equal to 0.5 inches squared, which is equal to 0.25 inches squared. And what else do we? So we got that. Our delta T. Our delta T is going to be 60 degrees Fahrenheit. It goes from 60 to 120. And that's about it. So our alpha is 6.60 times 10 to the negative 6 per degree Fahrenheit. Our delta T was 60 degrees Fahrenheit. So we'll just cancel out those units as we go. So now we got our strain. Times an area. So 0.25 inches squared times our Young's modulus. So our Young's modulus is 29 times 10 to the 6 pounds per square inch. And we'll just cancel out those square inches. So the number that we get here should be in pounds. And we're looking for a load. So at least the units we're looking for match what we should be getting. So 6.6 E negative 6 times 60 degrees Fahrenheit times 0.25 inches squared times 29 E6 pounds per square inch. Oops, I accidentally put 39. 29 E6. And that gives us a load of 2.87 kips. So we got our load here. So what they actually asked for was the average thermal stress. So that's going to be P over A. So that divided by 0.25 inches squared gives us 11.5 KSI. And that is a negative thermal stress because it is a compressive. Because it's a compressive force. The thermal expansion is going to want it to expand, and in order to resist that expansion, we need a compressive stress induced on the object. So yeah, that's that.